Hello, everybody, and welcome to today's spotlight series on 5G and wireless networks. Today, it's my pleasure to introduce Yi-Sung Chiu, that is currently studying a master's degree in NCTU and is doing research on 5G network infrastructure. And he has also had experience 2 times in the P4 brigade within ONF. And he's going to present his work on a cloud native management and orchestration framework for 5G end-to-end network slicing. So without further ado, let Stephen go ahead with this presentation, and thank you for joining us.
Hi, Andrew. Thanks for your introduction and thanks for having me today. So today I'm gonna to share our research in National Chiao Tung University in these several years. And our lab has been closely connected to ONF. We started from the ONOS controller, OpenFlow, and then P4's language, and also the mobile solution, which is M-Code. So we develop our own application with those open sources, and also we try to optimize the performance of M-Code by modifying the XOX framework. But recently, we tried to develop our mobile solution as we came to the 5G. So we still stick to open sources, but the different thing is that we try to be part of the community and do the contribution. So I'm really excited to be here and share our work recently. We use cloud native technologies to develop a management and orchestration framework for the automation of 5G end-to-end network slicing. Okay, so first I want to give a brief introduction of what is 5G network slicing and how 5G architecture looks like. Various applications are expected to serve by the 5G network, including the IoT service, automotive, which is IOV, Internet of Vehicle service, and also, of course, our mobile phones. And these applications have quite different service requirements in terms of bandwidth, latency, and other QoS demands. So for example, like IoT service may have large amounts of devices connect to our 5G network, but the traffic may be tiny. And for the automotive, we may require high reliability, low latency, and also security. And for mobile phones, we may have a larger volume of traffic. So here is a question: how could we serve these diverse requirements, service requirements, over a single and common 5G network? And here comes to a network slicing. A network slice is a logical network that provides a particular service for a use case. And at the right side, I have listed 3 types of well-known network slices introduced by 3GPP. And these 3 network slices are exactly correspond to the example I just take. So for mobile phones, we use EMBB, and for the automotive, we use URLC, and for IoT, we use MIoT service. So for the 5G architecture, we have radio access network components in the network view, and also with core network components for access, mobility, and authentication and accounting. And on the bottom of the network view, we have infrastructure view. Since we tend to deploy our functions with an FV in 5G, so we softwareize those function blocks and run on the top of the commercial off-the-shelf equipment or white box servers. On the top, we have the management view. So the management view performs the FCAPS management and also the robust automation for network services and network functions. So here we have 3 network slice management functions introduced by 3GPP. And also, since we use NFV, we have NFV MANO introduced by ETSI. So far, I think we get a complete overview of what is 5G network slicing and how 5G architecture looks like. And our work follows this 3-layer architecture and along with cloud native and NFV paradigm. So we propose a proof of concept for end-to-end network slicing, and the term end-to-end means from the user end to the service end. This including the three sub-network which are radio access network, transport network, and core network. So what we mean end-to-end network slicing, we means that we should slice on each of these three subnet, these three network. And for each subnet, we have their own sub-slice. And by interconnecting these sub-slice, we could form an end-to-end network slice. So for the radio access network, we're not yet included. We're now focusing on transport network slicing and core network slicing. And for transport network, we use SDN and programmable data plane to implement our slicing. For core network, we use 3GPP release 15 compliance functions. And those functions are software-based, so we can containerize those functions and deploy on our framework. On the top, we have the management and orchestration components. And these components is exactly the management view I just introduced in previous slide. So we perform the resource and service orchestration on this component. And we also expect these components to be manageable and observable. And with robust automation, we could easily orchestrate between each sub-slice to form an end-to-end network slice. And also, this is a face-to-cloud design. And all of these components, we use open source approaches. So this is correspond to the spotlight topic, 5G transformation with open sources. So first, I want to introduce how we slice our core network. On the bottom, we have the data plane from user equipment to the radio access network or GNOB, and then to a core network function UPF, user plane function, and then to the internet or data network. And on the top, we have the control plane. As we can see that the control plane in 5G is decomposed into several function blocks. And those functions interconnected with each other through a shared and common interface. We call it service-based interface, or SBI. And on the interface, we use RESTful API through HTTP and HTTPS methods. So as we can see in this figure, we have two slices, slice X and slice Y. And both sides have their own independent network functions, which are SMF and UPF. So here I want to go through a simplified procedure of how different slices of UE access the network service through these different slice components. So in these procedures, they may including some of the control message exchange and on the control plane. Yeah. So for the UE, first as it want to access the network service, it will ask for AMF to establish the session. And after the AMF gets such request, it will first ask network slice selection function to ask for which slice this UE could use. And after getting the slice information, it will ask network repository function for the SMF location. So here is the key points that how different slice of user could direct their traffic to different slice components. That is, AMF would direct the request to different SMF. And after the SMF establish the session on corresponding UPF, then user could access the network service through different UPF. So here is how we slice our core network. And as we can see, the core network have different resources between slices. Then here is how we deploy our core network with cognitive technologies. We use Free5GC as our core network function. So Free5GC is a open source 5G network project. And those functions are software-based, so we containerize and deploy on the Docker platform. Both Docker and Free5GC run on the top of commercial off-the-shelf equipment. And we use Kubernetes as our infrastructure orchestrator. For networking part, we use Calico as the interpart communication. And to be noted that since UPF is going to handle the data traffic, so we use hardware acceleration techniques on UPF interface, which is SRLV CNI. So next is how we slice our transport network. As we mentioned before, that transport network locates between radio access network and core network. So transport network is crosses N1, N2, and N3, three interfaces in 5G architecture. N1, N2 is the control channel between the MF and RAN, but N3 is the data channel between the UPF and radio access network. So what we expect our transport network slicing is, first we want to isolate the different the network resources between different slices. And second, we want to guarantee the control traffic, since we do not expect that control traffic would be starved when the congestion happens. And the third one is the most important one. We want to enforce the QoS requirements on user traffic. So here is how we differentiate the different service type of the user. So here is how we slice our transport network. We use P4 bandwidth management techniques. And this is also developed by our lab and was published on AP-NUMS 2019. So for more details, please refer to the conference. So here is how this technique works. As we can see, we use, as we mentioned before, we use the SDN and programmable data plane. And as the programmable data plane, we modified the basic pipeline. So we insert a meter.p4, which is a P4 program for bandwidth management. We insert it after the basic pipeline in ingress pipe. So here we have three tables, slicing, classifier, and parser. So how bandwidth management techniques work is, first, at slicing table, it would slice the different traffic, and in the classifier table, it would classify the packets and then assign to the different priority queue in the parser table. So with this mechanism, we could guarantee or limit the bandwidth in an exact rate. On the top of the control plane, we have several applications run on the ONOS controller. So we have reactive forwarding doing the forwarding jobs, and proxy up modified version of basic high conf and barefoot drivers, and also a main application, bandwidth management. So as an administrator try to slice the transport network, it will send a slice configuration through the RESTful API. And this RESTful API is also the ONOS config service provided by the ONOS controller. So when the bandwidth management application receives such configuration, it's then install the flow rules in these three tables through P4 runtime. So this is how we slice our transport network. So next is how we implement our management and orchestration framework. We use Kubernetes operator to implement such framework. Operator is a software extension provided by Kubernetes, and on the top we have end-to-end network slice operator. So this operator is going to orchestrate between two slice domains operator, which are TN operator and CN operator. So when we want to allocate the end-to-end network slice, we will send a request to end-to-end network slice operator. And the first thing it will do is validate the request and check if it is necessary to create a new end-to-end network slice. So if it is needed, it will first ask CN operator for the instantiation of the CN slice. So at this step, the free 5GC components would be created. And the next step, it will ask for the TN operator to configure our ONOS application for the TN slice. So as a step 3, so far we get the complete end-to-end network slice ready to serve our user. The next step is the final step to activate the new created network slice. So the end-to-end node size operator would update the node size information to the node size selection function. And for the upcoming user to use such size, it will ask for the NSSF to select the new created slice for it to use. And as we mentioned before, that we are not yet include the RAN slicing, and we want to slice the RAN domain as well. So in the future, if we want to orchestrate between the RAN domain, we could implement a RAN operator and connect to our end-to-end node size operator, then all is set. So this framework is easily to extend to other slice domain. So then is the evaluation part. First is the deployment time. As the left side, we have 3 items: MANO framework, including the 3 operators, creation of the 3 operators, and also creation of all nodes controller and connecting to P4 switches. And the other 2 is first and subsequent node slice. So all of this MANO framework and 2 slice functions are deployed on a single server with 40 cores and 128 gigabytes RAM. So as the right side, we have the deployment time in seconds. It takes about 1 minute and 10 seconds to deploy our MANO framework. And for the first and subsequent node slice, they take about 50 and 30 seconds to deploy. So the difference between the first and subsequent node slice is that for the CN slice, the first node slice requires to create shared functions, including AMF, SMF, and other common functions. But for the subsequent node slice, we only need to create the data key functions, which are SMF and UPF. So as we can see, that's the time difference between the CN slice is 20 seconds. And this is exactly the same difference between the first and subsequent node slice. So next is the evaluation of the resource overhead. And we have the same environment as the previous slide. And here we evaluate the memory and CPU resource. As the x-axis, we have time in seconds. As the left y-axis, we have memory in gigabytes. And as the right side, we have CPU load in %. So I'm not going to dive into details, but as we can see in 5 seconds, we installed the MANO framework, and there's no CPU occupation. But for the memory consumption increased about 1 gigabyte. So the reason why the MANO framework will consume the memory is because that's in this step it will instantiate the ONOS controller. So as we know, that the ONOS controller is a highly abstracted SDN controller, so it's consume memories. And for the first and second node slice, as you can see, the memory resource did not increase much, but for the CPU load, both sides have occupied about 2% or 3%. So the reason why the node slice would consume the CPU resources because 35GC implements the UPF instance with kernel module. So this can decap and cap the GPU packets. So here is why the CPU resource is occupied. So next is the service evaluation, and this is, I think, the most interesting part. As we mentioned before, that we use the bandwidth management on TN slicing. So this evaluation is try to evaluate if we could limit the downlink bandwidth of 2 slices, X and Y, with an exact rate of 5 Mbits per second and 10 Mbits per second respectively. So as I said, it limits the downlink bandwidth. So we limit we imposed 2 traffic on the service side. We have 15 Mbits per second on each side. And in the figure, as we can see, there's two lines fluctuate at the 15 Mbits per second. And after these two traffic pass the TN slice, as the SS side, we could receive these two traffic in an exact rate of what we just limit. So X, for slice X, there's 5 Mbits per second, and for slice Y, there's 10 Mbits per second. So this is quite amazing that we could limit the downlink bandwidth in such an exact rate. So as I mentioned before, that the bandwidth management could also guarantee the traffic when the congestion happens. So for more detail, please refer the conference. And in the future, we would like to integrate with commercial GNOB and UE, since there's no commercial equipment in the markets right now. And also we want to include RAN slicing in the future, and also extend our framework to Edge Cloud and MEC for low latency network services. And also we want to monitor for performance management. So for example, like if the resource is overloaded, we should perform the scale out to enhance the reliability. To summarize our work, we propose a framework for managing network slice lifecycle, and we use the state-of-the-art cognitive technologies and open sources. For CN slicing, we follow the 3GPP slicing mechanism. So currently, most of the end-to-end network slice research use 4G EPC as their core network, but we know that 4G EPC is not designed for network slicing, so they may have some workarounds and sacrifice some performance. For TN slicing, we enforce bandwidth control, and we could limit and guarantee bandwidth in an exact rate. And we also demonstrate that our deployment is efficient in terms of short deployment time and low resource overhead. So that's all I have today, and thank you.
Thanks a lot, Stephen, for your presentation. It was very, very insightful and a great amount of work. It's remarkable what you guys have achieved, both in the paper and with P4 and all the slicing that you have done. That's really good work. So, if you don't mind, I have a few questions.
Sure.
The first one is that you mentioned, I think it was slide 4 in your presentation, that the RAN side is not yet included. As you know, ONF is doing some work on that piece with the Ether project. Have you looked at integrating that as part of the RAN? Is that in the plans? What are your thoughts on that?
We're not integrating Ether Edge to our work. So basically, if the edge side want to connect it to the core side, they must have the same communication protocols. And as we mentioned before, that's the interfaces between the radio access network and the core is N1, N2, and N3. So basically, if these interfaces have the same protocol in Ether and in 3.5GC, then always work. But as I know, that's Ether use 4G EPC as their core network and 4G LTE as their radio access network. However, 3.5GC is a 5G compliant function, so it may not work for Ether Edge to be our edge site. In the future, if Ether migrates to 5G new radio, then the whole thing may work, but I think we still need further integration and field tests.
I see. No, yeah, that's for sure. I mean, it needs, obviously the standard is a big component of that, and having a common API, it's fundamental. And obviously then the integration and the testing, that's where the bulk of the effort lies in making sure that it actually works with what we expect. So, okay, I see. Yeah. Another thing, the same as you know, in ONF, and you have experience with us in the P4 Brigade, we have done a lot of work around P4. So I was actually curious, while you were integrating the meters and the bandwidth throttling with P4, have you found limits in the P4 architecture? Did this easily fit in the hardware within the constraints of like a Tofino chip, or was it difficult to achieve?
So to be honest, it's not easy to enable our application on virtual hardware on Tofino chips. So as we mentioned before that our P4 bandwidth management, we have 3 tables in charge of different things. Like slicing is gonna do the traffic matching. And for this table, there's no difficulty since that it's basic functionality provided by SDM. So we're simply matching the packet fields. So there's no problems. And for the classifier, we need to, so since we use token buckets mechanism to implement our classifier, we classify the packets. So at this step, we need to properly set the bucket size, the token bucket size, according to the traffic volume and burst size. Otherwise, the P4 metering may not work normally. So as an administrator, we have to be aware of what's our traffic in the slices in terms of the burst and volume. As the final tables, we have the policy. So what we do in the policy tables, we schedule the packets to different priority queue. And so in this step, we should properly configure the priority queues on the virtual hardware. And I would say that these configuration and settings takes us about a lot of time, and we have to do a lot of work to enable our bandwidth management on those P4 switches.
When you say it takes a lot of time, is that because it's not automated through P4 runtime? Is that because it's a proprietary Barefoot API? Can you elaborate a little bit?
Yeah. So like what I'm saying, that we need to configure properly on the priority queue properly on the Barefoot hardware. So actually, we spend a lot of time doing the research on how to configure the priority queues and let it work to assign the different packets to it.
I see. Okay, that's interesting. It's some good feedback. I think we can take this offline and maybe explore ways we can learn from what you have done within the P4 work at ONF. So that would also be awesome if you could upstream the meter.p4 and the applications that you have extended. That would be all great on top of ONOS, either in your repos, and then you can link them to the wiki, or within ONF itself. I think you can talk to Carmelo on what's the best option to upstream this. But I think metering within P4 is meter.p4, the one you have, could be a very interesting contribution to the ONF ecosystem, I guess. The last question I had was that, so you have a core network slice, and we're going more towards the 5G and the other parts of your work. You have a core network slice and a transport network slice that need to be interconnected. So exactly how to orchestrate this, like how you join the core and transport slices to get an end-to-end slice to achieve end-to-end traffic and functionality?
Yeah, so this is a good question that I didn't clarify much. So as I mentioned before, that how we slice our core network, we use the separation of the UPF instances, and how we differentiate the network traffic, we use the matching rule, provided by SDN. So since the different slice, for each slice, it may have its own data cake, UPF, and their own policy, bandwidth policy. So how we interconnect the transport slice and core network sub slice is simply we matching the UPF address in transport network. So basically, we're matching UPF address in this slicing table. And So for orchestration procedure, after we create our core network functions, the end-to-end network slice operator would access the UPF address. It will get a UPF address and then configure the ONOS application. Actually request the TN slice with those UPF address and bandwidth policies. So then TN operator could configure properly on the ONOS controller. So for the upcoming user to use the access the network service, it will send their data traffic to the DataK UPF. And those traffic would be matching by our configured TN slices. So that's how we interconnect to different subslice. That is TN slice and CN subslice.
I see. That's oh yeah, that's an interesting approach. Okay, yeah, it's pretty good, I think. So I'm done with my questions. If you have some final remarks, but otherwise, it was a great presentation. It was very insightful, and thanks for sharing it.
Thank you.
And we look forward to working more closely with you, both on the P4 and on the slicing side of things within our ONF projects.
Thanks for having me today.
Thanks a lot.